Welcome to Lecture 3.2. This particular lecture will introduce you to the idea of logarithms. We will find out that logarithms are inverses of exponential expressions where the variable. Go ahead. So we start out with the definition of a logarithmic function. And it's sort of two parts to it. It's more of a statement, if you will. And what it says is if b to the y, let me just make sure I'm writing this down. Yeah, b to the y is x. I wanted to make sure I followed exactly how your book said it. Then, if I want to write this same exact thing in logarithmic form, that would be log base b of x is y. Okay, so I know that looks really scary and probably confusing, but we'll make it clear as mud before the end of this lesson. I'll start out by saying that the base here and the base here are the same b's and are the same bases. So basically, if I have something that says log base b of x equals, and the b and the x being numbers, what you're really trying to figure out is what do I have to raise the base b to make x. So writing it in exponential form says I raise some b to some power and that gives me x. And if I have it in logarithmic form, log base b of x equals something, that's asking what did I have to raise that base to give me x. So let me just give you one numerical example, and then we'll move through these other examples of moving between the different forms. So if I have, I'll just write a little example here. Let me start out with the exponential form. Okay, I'll color code this. If I have a base, got the wrong pen. If I have a base of, let's say, 3, and I square that, that's going to equal some value. In this case, that value would be 9. So I could write that very same thing in logarithmic form by saying log base 3 of 9 is, so when you see this log base 3 of 9, it's asking the question, what can I raise the base 3 to give me 9? And so the answer there is 2. So I can write any exponential equation in logarithmic form. So that's what the first examples have us doing, just flip-flopping between the two forms. So this should be pretty quick and easy for you. When you're traveling through the logarithm, turning it into an exponential expression, You always start at the base, move to the is, and I call that the is because there's an equals between it. So base raised to the is equals the of, because that said log base 5 of x. So up here in general terms, this thing says log base b, pen froze, b of x is y. So that's how that's stated. So we always start at the base when we're changing from logarithmic to exponential. Start at the base, move to the is or the equals, and that's going to equal the of. Okay, so hopefully that makes a little bit of sense. So if I turn this into exponential form, it says 5 squared is x, and I could solve for x in that case. X is 25. You didn't have to solve, it just said to write the equivalent form, but that one was pretty easy to solve. Okay, this one is some log base b. So if I change, I start at the base, raise to the is, and that equals the of. So I start at the base, raise to the is, and that equals the of. Something cubed is 64. Well, if we took the cube root of both sides to solve that, we figure out that b is 4 there. So 4 cubed is 64. All right, this last one, start at the base, raise to the is, equal the of. So 3 to the y is 7. Now, this is where it's these situations are where it's necessary to know how to solve exponential, and logarithmic equations. Because 3 to the first power is 3. 3 squared is 9. So it's somewhere between 1 and 2. Now you could use your graphing calculator to solve this. So this is a little trick. If you want to use your graphing calculator to solve this, you would, for y equals, or y1 equals, you'd put in the exponential side of that equation, 3 to the x. You have to use the variable x on your graphing calculator. And then y2 equals 7, that's going to be a horizontal line. So you're going to get this graph for 3 to the x that looks something like that. And then y equals 7. And the x value where they cross, which is going to be 1 point something. I could go figure it out on my calculator if I wanted to, but it's 1 point blah blah. Would be the x value where those two functions are equal. So basically what we're going to be learning for the rest of this chapter and for the rest of the semester actually is how to solve these things without having to go and graph them on your graphing calculator, because you don't always have a graphing calculator, and it can be cumbersome to have to graph everything. So we like to have an algebraic way of solving these. So let's do the exact opposite of what we just did with turning logarithms into exponential expressions, and go the opposite way of turning exponential expressions into logarithms. So notice the base in this first one here is 12 raised to the second power. So when you write it as a logarithm, the base is going to be the same. And it's the base of the is equals the exponent. So remember, 12 squared is x, is our exponential expression. And whenever you're writing a logarithm, you write it of the form so that whatever you're equaling tells you the power that you have to raise to equal the logarithm that you're trying to take. But I probably didn't say that well at all. If this is confusing for you, just memorize this definition. I cannot express that enough. That if you can memorize this right here, you'll be fine, and how to move between those two things. So, log base b of 8 is 3. So b cubed is 8. And then this one, log base e of 9 is y. And I'll give you a little preview of what's coming up later in our lesson. You'll never see log base e. We have a special representation for a logarithm of base e, and that is ln. So we'll learn this in a moment, but the true way to write this would be ln of 9 equals y. So that ln is understood to be log base e, and I realize 100% I'm probably blowing your minds right now. I promise this gets easier. And once you understand it, it's really not bad at all. All right, moving forward. So just breaking down evaluating logarithms here. So once again, whatever base your logarithm is, this would say log base 2 of 16 right there. The question that it's asking me is, what can I raise to get 16. So if I have an equals question mark, that's saying what can I raise 2 to make 16? Or 2 to the something equals 16. All right, so 2 to the x equals 16. Well, x would have to be 4. And we'll figure out ways later. If you didn't see that, we'll figure out ways of learning how to do this. But I just know that 2 times 2 times 2 times 2 is 4 at this point. All right. Here is another thing that I would like to caution you about. When you have a power of the base, my base is 7 here. When you have a power of the base living in the denominator, you don't want it to stay down there. You want to bring it back up into the numerator, the realm that we like to work in. So the original question here says, what can I raise 7 to get 1/49? And I'm actually going to change that question. I'm going to go ahead and turn 1/49 into 1/7 squared. So whenever you can write a value as an exponential expression when you're dealing with logarithms, it's going to make things a little bit easier. And I'm not only just going to write it as an exponential expression, I'm also going to bring it up to the numerator where I like to work. So this is the same thing as log base 7 of 7 to the negative second power. And if you are not up to speed on all of your exponent rules, you need to go back into the prerequisite material and make sure you know those exponent rules backwards and forwards, because you're going to have to be able to know them and use them to be successful in this logarithm chapter. All right, so the new question is, what can I raise 7 to get 7 raised to the negative second power? Okay, so we have log base 7 of 7 to the negative second power equaling something. And the only thing that I can raise 7 to raise 7 to the negative second power is negative 2. So I would have to raise 7 to the negative second power to raise 7 to the negative second power. All right, so this next situation, my base is a larger number than the number that I'm trying to raise my base to and get. And the only way that can occur is if you're taking a root of a number. So what would be more beneficial is to change this back into, I guess it's pre-root taken form. So instead of taking log base 25 of 5, which says what can I raise 25 to get 5, I mean 25 to the 0 power is 1. So that's not 5. 25 to the first power is 25. So I'm going to have to raise 25 to something between 0 and 1. Well, that means I'm going to be raising to a fractional exponent, and fractional exponents are roots. So I prefer to look at this as log base 25 of the square root of 25. The square root of 25 is 5, so I haven't changed this thing. I've just made it look different. And I don't like to have roots either in my logarithms. I want to change that to an exponential expression. So this is the same thing as log base 25 of 25 to the 1/2 power. And if you're not up to speed on your rational exponents, you also need to go back and study rational exponents. I believe, if I'm not mistaken, that's prerequisite material 3 and 4 maybe, or 2 and 3, P2, P3, P3, P4, something like that. Okay, now the question is, what can I raise 25 to raise 25 to the 1/2 power? Well, the only thing I can raise 25 to raise 25 to the 1/2 power is 1/2. So log base 25 of 25 to the 1/2 power has to equal 1/2. Remember, I start at the base. Let me get a different color. I start at the base, raise to the is, and that equals the of. So 25 to the 1/2 power equals 25 to the 1/2 power. Okay, I'm going to change this one here. I don't like having that root there, so this is the same thing as log base 2 of 2 to the 1/5 power, because it's a 5th root there. And this is almost the same question, so I'm just going to put the little marks there that says same kind of question. This says log base 2 of 2 to the 1/5. In other words, what can I raise 2 to raise 2 to the 1/5 power? I'll mark it again. You're asking what can I raise my base to equal my 2 to the 1/5 power. Well, the only thing I can raise 2 to is 1/5 to raise 2 to the 1/5 power. All right, so we have some basic properties that jump out at us when we start looking at logarithms. Log base b of b. This says, what can I raise b to get b? The only thing that I can raise that to get b is 1. So log base anything of itself is always going to be 1. So the reasoning behind this is because b to the first power is b. Okay, the next one, log base b of 1, says what can I raise my base b to make 1? Well, the only thing that you would be able to raise any base to and get 1 out is the 0 power. That is because b to the 0 power is 1. So I'm justifying these logarithms by changing them into exponential expressions. Okay, so this next one, we've already taken a look at a couple of examples above. This says log base b of b to the x power. In other words, what can I raise this base b to raise b to the x power? Well, that's x, because b to the x equals b to the x. And this last one, the last one's a little tricky. I'm going to start out with a true statement. I'm going to do this in a different color since this one's a little trickier to explain. And it's really not that bad if you start out with this true statement. It's like, oh, okay, that makes sense. So log base b of x has to equal log, freezing again, log base b of x. So anything equals itself. And if I use the rules of changing back to exponential, changing to exponential form, I start at the base, raise to the is, and that equals the of. So b raised to the log base b of x has to be x. So this is x here. And that's the reason why. So anytime you raise a base to a logarithm of the same base, your answer will always be whatever's sitting in the of position of the logarithm in the exponent. Okay, moving forward. So we have some logarithms here that we are asked to evaluate without using a calculator. And the reason we don't need a calculator is because we can change all of these to very simple logarithms that we can do in our head. So this first one says, what can I raise 4 to make 16? Well, that's got to be 2, because 4 squared is 16. All right, this next one I'm going to change because I don't like having the power of 2 sitting in the denominator. So this is the same thing as log base 2 of 1 over 2 cubed. And once again, I'll bring it up, log base 2 of 2 to the negative third power. So it comes up to the numerator and becomes negative. So now the question is, let me get a different color here. It's asking, what can I raise 2 to make 2 raised to the negative third power? So the answer there is negative 3. All right, next one. I'm going to change this as well to be log base 6 of 6 to the 1/2 power. Okay, the question now is, what can I raise 6 to make 6 to the 1/2 power? This is why we didn't need a calculator. It's just 1/2. You just have to know your exponent rules and your definition of logarithm to be able to do that. All right, log base 64 of 8. So I'm trying to raise 64 to a value to make a smaller value, so I know that rational exponents were involved. Okay, so 8 times 8 is 64. So 8 squared is 64. So this would be asking the same question, log base 64 of the square root of 64. Because the square root of 64 is 8. I could change that further and say log base 64 of 64 to the 1/2 power. And now the question becomes, what can I raise 64 to get 64 to the 1/2 power? And that is 1/2. All right, the next one. This says, what can I raise 4 to make 1? Well, the only thing you can raise any value to get 1 besides 1 is the 0 power. And this last one, remember with our rules, I said if you're ever raising a base to the logarithm of that same base, the answer is always what's sitting in the of position. So this is just 23. And that is using our basic properties of logarithms there. All right, your calculator. You have a button on your calculator. Because there are infinitely many bases that you could be working in, your calculator can't store enough data. Enough algorithms to work in any base possible. So your calculator works in 2 bases. And the first one is just your log key. So whenever you just see log and no base written, this is known as the common log. And what this means is that there's an understood base of 10. You don't see it, but it's there. So if I have something like log of 100, that is asking the question, what can I raise 10 to make 100? Because 10 is understood to be there. I'll write that in green. The 10 is understood to be there. So 10 raised to the what power is 100? The answer there is 2. So the log of 100 is 2. And you could take your calculator and literally type in. Okay, so the log key is right here on the left-hand side of it. And if I do log and I type in 100, careful with your parentheses on these, so I had to close those parentheses off. The log of 100, and I hit enter, you can see that I get the value 2. So the log of 100 is 2, because it's understood that it's working in base 10. So let me just remind you of your general properties that we just went over. Log base b of 1, well, b raised to the 0 power is 1. Log base b of b raised to the first power is b. Log base b of b to the x is x, because b raised to the x power is b raised to the x power. Log base b raised to log base b of x is also just x. So these are our general properties. We have those same properties for common log. So the log of 1, remember that's understood base 10. So what can I raise understood 10 to make 1? 0. Log of 10, that's log understood base 10 of 10 is 1, because 10 understood 10 raised to the first power is 10. And this last one was understood 10 raised to the 0 power is 1. Log understood base 10 of 10 to the x is x, because understood 10 raised to the x power is 10 to the x. And the last one, 10 raised to the log of x, that's an understood base of 10, so 10 raised to log base 10 of x is x. So we can evaluate these next ones without using a calculator as well, because they are all, in some form or another, powers of 10. So log of 1,000, here's another little trick. However many zeros are on the end of a power of 10, that's what power it was raised to. So log understood base 10 of 1,000 is 3. That's because 10 cubed is 1,000. So whatever power you've raised 10 to, that's how many zeros are going to be on it. So you don't even have to go to your calculator for those. Okay, log of 1 over 100. I've already said you don't want to have anything living in the denominator, so bring it up, give it a negative exponent. This is the same thing as log of 1 over 10 squared, which is log of 10 to the negative 2. That log is an understood base 10. So what can I raise 10 to? To raise 10 to the negative second power, and that's negative 2. The log, I should have had parentheses here, of negative 10. So let me tell you what this is asking you. This is saying, what can I raise 10 to give me negative 10? Now, there is no exponent that you can ever raise a positive number to and get out a negative number. It's not a negative exponent. That kicks it down to the denominator. It does not make the number negative, because it's not multiplication we're talking about. So, 10 raised to the something power gives negative 10. This is not a real number. And let me see how your book states this particular example. Like I said, it's not that I don't know this, I just don't want to deviate too much from your book, since students tend to get confused with logarithms. I made this problem up, so very good. If you put it into your calculator, the log of negative 10, you're going to get a non-real answer. So okay, let me see if I can Hope you see that a little bit better. Okay, so you see at the top it says error, non-real answer. So you can just write not real. We're not going to talk about imaginary exponents and things like, don't even worry about that, just put not real. It's not undefined. It is defined, it's just not real. So you're going to write not real for things like that. All right, log base, understood base 10 of 1. So what can I raise 10 to make 1? Well, you raise anything to the 0 power to get 1. 10 raised to log understood base 10 of 52 is 52. And 10 raised to log understood base 10 of the square root of x is just the square root of x. Okay? We have 2 more slides to go. Okay, so this is the next button that you have on your calculator, LN. And I already told you at the beginning of this lesson what this button actually means. So just like log was log understood base 10, LN is equivalent to log understood base E. And we talked about what E is. E is the natural base. We talked about that in lesson 3.1. So if you skipped over that and you're like, what the heck is E? Go back and watch 3.1 lesson, and that will make sense to you. So E is an actual value. It's a limit that is approached with 1 plus 1 over n raised to the nth power as n moves into infinity. And once again, if that's gibberish to you, watch 3.1 lecture. All right, so we're going to review those general properties again and see that they, actually this should say natural log. Sorry, natural log. See that they apply to the natural logs as well. So log base b of 1 is 0 because b to the 0 power is 1. Log base b of b is 1 because b raised to the first power is b. Log base b of b to the x is x because b, log base b raised to the x power is b to the x. And b raised to the log base b of x is x. All right, ln of 1. So I'm just going to rewrite this for understanding purposes, but no, this is not how you write this. Whenever you're talking about log base e, you write ln. But this is the equivalent of log base e of 1, which is 0. And that is because e raised to the 0 power is 1. The next one, ln of e. That's the same thing as log base e of e. Well, that's going to be 1 because e raised to the first power is e. Next one, once again, you don't write log base e. I'm just doing this for teaching purposes. The ln of e to the x is understood to mean log base e of e to the x. Well, that's going to be x because e raised to the x power is e to the x. And the last one, e raised to the ln of x is just x because that's the same thing as e raised to the log base e of x, which is x. All right, so some more that we don't need our calculator for. The ln of 1, we've already looked at that. That's 0. Log base e of 1 is 0. The ln of e to the 4th, I want to bring that up to the numerator. This is the same thing as the ln of e to the negative 4th, which I'll rewrite this with log. This is the same thing as log base e of e to the negative 4th power. Well, that has to be negative 4 because e raised to the negative 4th power is e to the negative 4th power. and this is the ln of negative e, that's the same thing as asking what is log base e of negative e. Once again, this is not real, because you can't raise the real number e to any exponent and get a negative value out, because e is positive. The ln of e squared is the same thing as log base e of e squared, and that has to be 2, because I would raise e to the second power to raise e to the second power. And the ln of e raised to the 7x squared, that's the same thing as log base e of e to the 7x squared. That has to be 7x squared, because e raised to the 7x squared has got to be e to the 7x squared. And finally, e raised to the ln of 6 is the same thing as e raised to the log base e of 6. Well, that's got to be 6. All right, some challenge. So these are logarithmic equations, and the way we solve logarithmic equations is to change them, well, these type of logarithmic equations is to change them back into their exponential form. So what this is asking us is 3 squared is equal to x minus 1. 3 squared has to equal x minus 1. So 9 equals x minus 1. Add 1 to both sides. 10 is x. Easy enough. And you can check it by plugging it back in, since it's an equation. So log base 3 of 10 minus 1 equals 2. Log base 3 of 9 is 2. And log base 3 of 9, 2 equals 2. Checks out. All right, this next one, 4 to the negative 3rd power equals x. Okay, well that's the same thing as 1 over 4 cubed, once again using our exponent rules, and that's 1/64 equals x. And this last one, 64 to the 2/3 power equals x. So here's our rational exponent stuff that we have to know here. 64 to the 2/3 power is the same thing as the cube root of 64 squared. Okay, I still don't like working with 64 squared here, so I'm going to change it even further so I don't have to touch my calculator. 64 is the same thing as 8 squared. It's the same thing as 4 cubed. I'll go with 4 cubed. So this is the same thing as 4 cubed squared. I could have put it in 2s. It's the same thing as 2 to the 6th power as well. So here I really have the cube root of 4 to the 6th equals x. I can break this up because the only thing I want to take cube roots of are the things that are cubed. So this is the same thing as cube root of 4 cubed times cube root of 4 cubed. Well, whenever I take the cube root of anything cubed, it's just that thing. So I have 4 times 4, 16 is x. All right, don't forget, Unit 6 quiz will be over 3.1 through 3.4. That homework and the quiz are due Monday, April the 28th, so we still have almost 2 weeks with that. But go ahead and do your homework. Don't let this all pile up on you. And I know it's late in the game, but some of y'all have really just been pushing it to the last moment to do all your homework and your quizzes. And pretty much when you do that, your grades suck. So the ones that are successful are the ones that are watching the videos as I produce them and going ahead and doing your homework. So please do what you know you need to do, and that's keep up with things and not let them pile up and overwhelm you. That quiz will be open on Thursday the 24th, like it always is on Thursdays, or the Thursday before it's due. Next lecture is next Monday at 3 p.m. I'll cover section 3.3, and don't forget, fall registration is open. Please make sure you are registered for fall classes. Thanks. Have a great day.